Okay, so here we go. Last time we were talking about differentiability, you may recall. So the big idea is, we have this formula for linear approximations, and we have to ask, is that actually doing the job that we wanted it to do, or did we just accidentally write down a bunch of garbage because it seemed right? So there are some nasty questions here, as it turns out, right? And we've already been through this page and half of the next page, so I'm going to go quickly through this. But we do have to worry about it. And we saw an example here where the formula that we came up with, right, that seemed so reasonable, as we approach, the origin for this particular function, that linear approximation, air quotes, linear approximation that we wrote down, has values that are uniquely 1, right, a constant 1, and yet the original function has values that are not, right, anywhere along this purple line going at an angle toward the origin. Right? So if we ask, okay, well, what was the error? How far was this off? Well, these errors are all 1, and that's obviously not a good approximation. So we move on to the idea, well, hey, maybe it's good enough to just ask that the error approach 0. And then we saw this example here where we see that no, having the error approach 0, as we saw in this case, would suggest that this is a good linear approximation of that, which again, obviously isn't. I mean, if we're going to define some notion of what we mean by a good linear approximation, that better not be it, right? I mean, we don't want that, right? So this is not good enough either. Right. So again, what it turns out to be the best answer is, and I'm leaving out a lot of stuff here. Of course, this is the very, very quick and dirty treatment of this idea. But we consider instead this idea of relative error, and relative error is not just error; it's error divided by how far away are you from the base point at where you're doing your approximation. And even though the error approaches 0, as we saw previously, the relative error approaches not 0 here. So this idea of vanishing relative error, the error is not good enough to look at, the relative error has to approach 0, is what we have to resort to get a definition that actually quantifiably rejects this obviously bad linear approximation, right? So in some sense, we have to resort to this. Otherwise, we're stuck with nonsense. Okay, and I put this switch off. There we go. So this is where we left off last time, and picking up from there, I'm going to point out that that's where this big, bulky, scary-looking definition comes from. This expression here. This is just a way of saying vanishing relative error. That's all it is. You can see so right here. There's relative error. Right? Don't forget that error, right, is actual minus estimated. And don't forget that the estimated, right, and I'm going to real quick come over to here, and I'm going to put some parentheses around this and make this a plus, because don't forget that the estimated, right, the linear approximation is what that is. Right, so again, that's all this is. This great big scary looking expression is just a fancy way of saying I'm going to look at relative error and I want to require that to approach 0. So that's where differentiability comes from. Why do we care, by the way, about this particular worry about differentiability? And this is another deep question I'm going to have to kind of largely gloss over. But it turns out that this notion of differentiability, right, not good enough to simply have the partial derivatives all computable, right? Remember, in this example up here, the partial derivatives are all fine in this example, right? So being able to compute partial derivatives is not that meaningful Don't be impressed by partial derivatives. Yet another reason I don't like partial derivatives. Why it is that this notion of differentiability is important has to do with other theorems. And it turns out there's a bunch of theorems that we're going to write down in this course that have to do with derivatives and, under what conditions does blah blah work out, and what is the precise, sharp requirement to make it work. Differentiability, as it turns out, right? And again, as it turns out, I'm glossing over lots of deep water. Okay. All right, so that's what differentiability is. Real quick, another different point of view on this. Again, we've made the observation that we have actual value of the function minus estimated value of the function, again with the parentheses. Sorry about that. But I do like to point out that there is a different way to group these terms together. You can take this exact same numerator and group it instead as, I wanted to change the color there. You can group it instead as how much did the function actually change, which we call the increment, minus how much did we estimate the function changed, otherwise known as the differential. So you can think of this again as actual value minus estimated value, or you can think about it as actual change minus estimated change. Take your pick. They both make sense, and of course they're totally equivalent. Okay, all right. Heads up on these terms. Be aware of these terms. I'm going to feel free at this point to use the term increment and the term differential. They're natural and common terms. Yeah.
Is the test also that the difference between the two approaches zero as you approach it?
Yeah, exactly. So we want, let's see here, I'm going to have to use a different color. Relative error approaches zero. Yeah, absolutely. That's the requirement. Exactly. Okay, so moving along. Does this mean that if we want to know when a function's differentiable, we're going to have to use that great big bulky definition? Thankfully, in most cases, no. In most cases, there's a much easier way to conclude when a function's differentiable. And it has to do with a related condition called continuous differentiability. Function being continuously differentiable, which is a stronger condition. Weirdly, it turns out that even though continuous differentiability is a stronger condition, it is way easier to define. Way easier. And it's nothing to it. It's just two things. I need the partial derivatives to exist and be continuous. That's it. It's shocking how simple this is. By the way, I've already kind of trashed the idea of, hey, don't be impressed if your partial derivatives exist, right? With our very first, most preposterous example, the partial derivatives existed, right? So that's not impressive to have partials exist. The mere additional requirement of continuity, that the partial derivatives not only exist, but that they are continuous, gives you this very strong condition, continuous differentiability, that we love because of this theorem right here. If a function is the easily checked continuously differentiable, then the function is also differentiable. And we get to conclude the result of that great big nasty discussion about vanishing relative error and all that stuff. We don't have to do any of that. If the function is continuously differentiable, then it is also differentiable. Which, by the way, brings up the question, well, why do we talk about differentiability in the first place? And the answer there is just that there are some functions that are differentiable that are not continuously differentiable. And now we're getting into the sort of the weirdo, delicate, deep water stuff that we're going to gloss right over. We're going to sail right over it in Math219, and in other deeper courses on multivariable calculus like Math219. They'll talk more about those scary monsters. Okay, so different ideas, but the continuously differentiable is much easier to work with. So, for example, here's a question. Is this polynomial differentiable? And again, the definition of differentiable is that big expression on the previous page talking about relative error. So, does this function have that property? Well, it turns out it's really easy to answer this question. The partial derivatives of this function, I don't even have to write them all down. I can make a casual observation. Well, look, this is a polynomial. Obviously, its partial derivatives are all polynomials. That's just, clear, I hope, right? Okay, here's the thing. Polynomials are continuous. Old fact, right? Which means, therefore, that all of the partial derivatives are continuous, which means the function is continuously differentiable. And then by the above theorem, it follows that it's differentiable. And we're done here, right? No relative error, no confirming that it vanishes, right? Much easier, just kind of casual observations. Everybody see how this works? It all hinges, of course, on this big theorem right here that continuously differentiable always implies differentiable. Okay, so nice tool. That's what you're going to be vast majority of the time, right? This is how you confirm differentiability. You confirm continuous differentiability. Okay. All right. Here's another useful fact. Every differentiable function is continuous. If you kind of change the sort of, I don't know if you'd say active tense to passive tense, or I don't know, something along those lines. Same exact statement, but just kind of said sort of backwards and upside down, if you will. If it's not continuous, and it's definitely not differentiable. It's called the contrapositive, by the way. I don't know if you all have seen that before. It's a good fact to know. If A implies B, then not B implies not A. And I think it's pretty cool. So, okay, anyway, what we have here is a theorem that allows us to draw a conclusion about differentiability. There is a condition that I can check. Just look to see, is the function not continuous? If this condition is satisfied, then boom, conclusion. That function is not differentiable. Right? So nice in that this is, a tool that lets us draw a conclusion about differentiability. So let's look back at our original function. How would I, this weirdo, right? How would I conclude whether or not this function's differentiable? We obviously don't think it should be, right? Not only does the vanishing error, not only does the relative error not vanish, the error itself doesn't even vanish, right? But notice, we don't have to bring any of that up. It's much easier just to observe this function is clearly not continuous, right? Just look at the picture. It's got this big jump discontinuity in several places, right? It's specifically at the origin. Right? Big jump discontinuity. So not continuous, and that means not differentiable. And game over. Okay, nice little additional tool. Okay, so moving along now, we're going to talk about the derivative. You may recall I started last week, I guess it was, when we were first talking about multivariable derivatives. I pointed out there's actually a bunch of different kinds of multivariable derivatives. We've seen most of them, not quite all at this point, right? So there's partial derivatives. There's the gradient, right, which is a different thing. There's the derivative matrix that we wrote down. Okay, and we're going to see another kind of a derivative coming up pretty soon. It'll take us a few days. So what do we call the derivative of these three that we've seen so far? And what I'm going to answer that question is by reminding us about linear approximations, right? So linear approximation is computed by this formula. Now, quick reminder, this is just kind of a borderline throwaway point, but this is the formula because it meets certain requirements, and one of those requirements is that the linear approximation has to actually equal to the value of the function at the point where you're doing your approximation. So by design, f of a is L of a. And with that noted, I can take this L of a and move it over to the other side of the equation. All right, subtract it on over. And then notice what this expression has turned into. Right, this equation has turned into a pretty powerful statement about what this matrix does. This matrix multiplies by what I'm going to call the input differential. How much am I changing my input value? I was looking at the point A. I'm now asking what happens when I move over to the point X. How much did I move? What was the displacement in the domain? This difference, right? So that's the input differential. How much did I change in the input space? And apparently, according to this equation, df multiplies by the input differential to produce the output differential, which you'll recall we defined a couple pages back. Right? In other words, the output differential is how much are we, based on the linear approximation, what is our estimate of how much f changes? Estimate, to be fair, not the actual change, but our linear estimate of how much it changes. So you can rewrite this then pretty powerfully as df is what you multiply by dx to get df. The df matrix then, here let me highlight this like this. df is the thing that you multiply by input changes to get output changes. And again, first thing I wrote down in the chapter 2 notes is that this fundamentally is what a derivative is. Every derivative you've ever seen fundamentally has this property. It turns input changes and output changes some way or another. And this is about as general as you can get in that if you're talking about multivariable functions. In fact, vector-valued multivariable functions, right? No assumptions on the right-hand side here about, all the other variables are constant. What a weird construction if you really think about it. Let's just assume. How often is it in life, by the way, that only one thing is changing? Right? That's not how it works. Everything's always changing. Right? So, completely general notion of input changes, whatever it might be. And the matrix, df, is what turns that into the corresponding output change. So this is what we call the derivative then, right? df, because it is the most general thing that does what derivatives do. So sometimes we call it the derivative matrix, just to be clear. Sometimes we call it the derivative transformation if you, for whatever reason, feel the need to think of this as being a linear transformation, which of course it is. Right? If you prefer to think of it as a linear transformation as opposed to a matrix, whatever. Right? They're basically the same. Okay. And then heads up, it is also sometimes written as JF. And this is a reference to the fact that this matrix is sometimes called the Jacobian matrix for kind of historical reasons, which, sure. And by the way, again, in my mathematical upbringing, it was called the Jacobian matrix a lot. And so you're going to hear me accidentally saying Jacobian matrix here and there. When I accidentally say Jacobian matrix, I mean this thing. I mean the derivative matrix. Okay. All right, so that's what a derivative really is. Here's a picture of it, in sort of what I call the literal picture of a function. If you have a function that takes, let's see here, color choices. If you have a function that takes an input point in the domain to an output point in the target, keep in mind what a function does. It takes inputs, gives you outputs. the derivative matrix is the thing that takes not inputs, but input changes and turns them into output changes, right? So the derivative transformation doesn't take points to points. It takes, you might say, vectors to vectors, changes to changes. Does that make sense? Are you happy with that? Okay. Now, that's a really nice way to think about it. Here is a different way of saying it. Let's suppose we take our existing equation that we already have, right? This is what we already have. And now let's just divide by dt, right? Just on both sides of the equation, just divide by dt. And again, I don't want to get formal and rigorous about this. That's not what Math219 is about. But notice that if I do so, perfectly legal, right, satisfying anyway, notice I get a different interpretation of what the DF matrix does. The DF matrix now takes velocity, input velocity, multiplies by that input velocity, and the result then being the output velocity. So again, it's kind of an input changes to output changes kind of a thing. It's just that now what DF is doing is taking in an input rate of change and producing an output rate of change, right? So a little bit of a tweak on the original point of view. What I like about this is that I get to throw away the word approximation, right? I mean, to be fair, DF does not tell you exactly how much the function changes. It's just our linear estimate, right? This does away with that. If dx dt is the input velocity, then df dt is exactly the output velocity. Is that cool? Everybody happy with that? Yeah. Flashbacks to single variable calculus. So this last little bit here is really just an observation of a sort of a notational alternative. Let me remind you what we did up here to get to all of this is we took our formula for linear approximation and we kind of just moved things around a little bit. DF was a part of our original equation and ends up then being the sort of the center of focus of the result. So all I'm doing down here is pointing out that when you're talking about real valued functions, you have the option of, instead of using the derivative matrix, you can use dot product with the gradient vector. It's just a different way of writing it down, right? And if you do that and kind of follow it all through, you get to this same result. I should use my colors better. That the gradient vector, specifically dot product with the gradient vector, is what multiplies by input changes to get output changes. Right, so that's a different way to think about it if you prefer. Now, really, it's not that different. I mean, dotting with a vector whose elements are all of the partial derivatives versus matrix multiplying by a single row matrix whose elements are all of the various different partial derivatives. It's the exact same elements, right? It's just kind of it's a different take on what's ultimately the exact same algebra. So feel free, take your choice. You can think of this as dot product with a vector. You can think of this as matrix vector multiplied by derivative matrix. It's really all the same. Okay. So same interpretation. And again, all of this is only if you have a real valued function. But when you have a real valued function, you can think of it instead as being dot product with the gradient as opposed to matrix product with the derivative matrix. Okay. How are we doing? Everybody happy? Okay. All right. Okay. The section 2.4 is full of a bunch of stuff y'all can totally read. So I'm going to let y'all read most of that. Do make sure to go through, make sure you're good with all of it. As of course in a lot of the rest of the stuff that's in this course that I tough choices and all that. So old news. We know that the derivative, it's a matrix. It multiplies by vectors to give vectors. Being as a matrix, it's obviously linear. No problem. Okay. Here's a similar sounding but very different statement. It's not just that the derivative matrix is linear. I claim that the act of differentiation is also linear. Very different statement. Let me be clear about what I mean by this. If you have a differentiable function f, the act of differentiation, right? Applying this d to it, with that thing that turns, a function into a matrix. Right? I'm saying that this process of turning a function into a derivative matrix is also linear. Totally different statement. Does everybody see the distinction I'm talking about here? Right? So D now is I'm claiming a linear transformation from the vector space of differentiable vector value multivariable functions into the vector space of m by n matrices. All right, so that's a substantial statement. So when I claim that D is linear, what I mean is this. And notice what this is doing. This is taking not a linear combination of vectors, right, to which I'm applying a matrix. No. This is a linear combination of functions. And I'm saying, what if I were to apply the act of differentiation to this linear combination of functions? And the claim is that what I get is that same linear combination of the derivatives of the original functions. Yeah. So what does this look like? Here you go as an example. And there's just a bunch of details in this example. It's pretty straight reading, so I'm just going to hit the highlights. But what we have here is a couple of functions, and their derivative matrices easily computed. Right? And then I'm going to look over here at what happens if I take a linear combination of those functions and look at the derivative of that linear combination of function. Now again, this is a matter of multiplying it out. This is the linear combination of those functions. And here's its derivative matrix. By the way, make sure you can do all this. Make sure that you are comfortable with all the sort of processes that I'm glossing over there. And here's the linearity. The linearity is the claim that if I look at the, let's see here, why don't I erase this? If I look at a linear combination of the derivatives, or if I instead might look at the derivative of the linear combination function, that we get the same thing. So you can see here how that looks like a statement about linearity. Right? There's that linearity statement about D. And you can see here how the arithmetic clearly works. And it's just a matter of writing down the numbers. Okay. Everybody okay with that? All right. There's a few other facts in the section that make sure to read everything in the book here. There is a kind of a product rule of sorts, right? And there is a kind of a quotient rule of sorts, and so it's pretty much exactly what you would expect. Just make sure to read it. Make sure to be clear on which rules apply and when they don't. But when they do, that's exactly what you would think. Okay. All right. Moving on to higher order partials. Y'all recall, I'm sure, that when you have a single variable function, you take the derivative, the result is a single variable function, which is something you can entertain taking another derivative of. right? Well, the exact same thing happens with multivariable functions. If you have a function of several variables, and if you take a partial derivative, right? If I take a partial derivative of that single variable function, well, good news. This partial derivative is also another function of the exact same variables. And it's easy to observe this happen. Here is a multivariable function of x and y, and check it out. When I take its various partials, I'm going to take the x partial, let's take the y partial, work out the numbers, y'all can do that. Notice that these partial derivatives are also functions of the same variables x and y. I mean, stands to reason, doesn't it? Everybody okay with that innocent observation? Being as these are more functions of x and y, we can then very reasonably ask the question, well, what happens if I want to take partials of them, right? So here, I'm just going to focus on the left-hand side here. Here we have a function of x and y, which is called fx, partial of f with respect to x. But the fact that it's a partial of something, don't worry about it. It is itself a function of x and y. And I can therefore talk about what happens if I take its x partial or its y partial. All right, now there's some notation to talk about here. It's kind of annoying. It just is what it is, though. How would I write the y partial of this x partial? And there's a couple of perfectly reasonable choices. We started with the partial of f with respect to x, and we're taking the y partial of it. Right? This is our notation. If you're going to take a y partial of something, y partial goes on the left, and the thing you're taking the partial of is on the right. And so unavoidably, from sort of this point of view, if you're going to write this with a single notation, the kind of the y is on the left and the x is on the right, and thus this notation. But frustratingly, let's see. Oh, did I just make a mess? I can't. I got it. Okay. Frustratingly, our other notation, if I use the subscripts, I take the x partial still first, and how would I represent the y partial of that? Well, that is another subscript, which of course, per our convention, on the right this time. Right? So notice the y partial is kind of written on the left with the one notation, it's written on the right with the other notation, and these can't be helped. Right? This is intrinsic to the notation that we're working with, and I say it can't be helped. I suppose one possible resolution of this seeming backwardsness would be to get every working mathematician and engineer and physicist, etc., to all agree that we're going to go back through all of our work, we're going to go back through all papers that have ever been written using these notations, and we're going to change all of them. It's absolutely unfathomable, right? That's never going to happen in a million years. And so we're just stuck with this, oh my gosh, right? How annoying is this, that these seemingly opposite orders are actually representing the same processes. So heads up, all right? You got to be careful with this little circumstance. It's anyway. Okay. Everybody okay? Right. Okay. So now you'll notice here, perhaps, that here let's see. I'm going to zoom out so I can kind of fit everything in here. In the process of writing all this down, on the one hand, I did an x partial and then a y partial, and on the other hand, I did a y partial and then an x partial, and oh my gosh, what are the odds? I got the same thing, weirdly. Right? Now those are two different processes, the x partial, the y partial, the x partial. What a coincidence. Got the exact same value. It's probably not hard to persuade yourself. If you think about the formula for how you compute partial derivatives of polynomials, that in some sense only one factor at a time actually is doing anything. And so this is pretty easy to persuade yourself will work for any polynomials. But harder question, does this work for not polynomials, where there is no such sort of immediate argument? And as it turns out, yeah, it actually usually works. Not quite always, but usually. And here is the full statement of this fact. There is a big condition. The function has to be what we call CK. CK, this is a regularity condition. It means the function's got to be nice in a certain sense. And specifically, CK, the K refers to how high of an order of partial derivatives do I want to talk about and put a requirement on. And the C stands for the fact that I need all of these kth order partials to be continuous. So again, it's just kind of a notational sort of choice. Again, K is a reference to kth order partials, and C is a reference to them having to exist and be continuous. So a lot of functions are CK for various different values of K. By the way, there's such a thing as C infinity. A function is C infinity if you can take all the partials you want and it just keeps being continuous. So you could imagine like exponentials, like e to the x or e to the x plus y, something like that. Just keep taking partials over and over and over, and they just keep being continuous. And no matter how many partials you take, we call that a C infinity function. So, anyway, most functions that you write down with convenient convenient functions that we do business with most of the time, they're mostly C infinity where they're defined, which is very good news. Anyway, that's the condition. And if that happens, then yes, you can reorder your differentials down at the bottom all you like. The order that you do the partials doesn't make any difference. Okay? Any sort of a rearrangement, all good. It's a little bit clunky to write that down, and so that's the clunkiness of how this is written. But the punchline is, take the partials in whatever order you like, no problem. Okay. All right. What do they look like? Right. So again, you can define anything you want, but once you've defined it, you owe your listeners, your readers, an explanation of why they should care about it. Otherwise, it's just symbolic nonsense, right? So why do we care? What geometric meaning, what use can I make of higher order partials? Well, let's think about fxx, for example. fxx says, first I'm going to take the x partial, and then having done that, I'm going to take another x partial. So the thing about it is, if you're taking an x partial, that means you're going in the x direction, which means that you're treating y as a constant, which means you're looking at this cross-section. Right? If you think about it, the first x partial that we take is going to give us the slope of the tangent line to this purple curve. And then the second x partial, again, we're going to treat y as a constant. We're going to be looking at the exact same curve. Another way to say it is fxx you can compute by setting y equal to a constant, thus looking at this curve, and then just literally taking the highly familiar single variable second derivative of that purple graph that we're looking at there. And of course, we know what that means. That's just a statement about concavity. So fxx, per this picture, apparently is negative, because I can just see right there that the concavity on that graph, as I'm pointing in the x direction, that concavity is concave down, and so negative. Familiar? Right? Relatable? Good news? Everybody happy with that? right. So related, and I'll say analogous thinking. If we want to talk about FYY, that means we're looking in the Y direction. That means that my cross-section looks like that. And second derivatives, concavity, and all of that. And apparently the Y, second partial, positive. That's concave up. Totally analogous argument. Everybody cool? Yeah. All right. Okay. Here's what gets tricky. Not every second partial is, just with respect to one input. As we saw on the previous page, sometimes you might want to do what's called a mixed second partial. So here I'm doing a Y partial, and then having done the Y partial, to the Y partial, I'm then going to take an X partial. Right? How would I make sense out of this? What does this look like? And this is a tricky bit. By the way, there is no single variable version of what I'm about to show y'all here. This is something that only comes about because there are different variables with respect to which I might take partial derivatives. Right? Single variable, there's only one variable. There is no such thing as a mixed derivative. Right? So, okay, what we're going to do here is we're going to have to take advantage of our different points of view on derivatives. So I'm going to take, for this Y partial, I'm going to take a slope of the graph point of view. Okay. The X partial that I'm going to do of that, I can't take a slope of the graph point of view. If I were going to take a slope of the graph point of view on this X partial, if you think about it, I would need a graph of the thing I'm taking the X partial of. I would need a graph of the Y partial of F. That's not what I'm looking at. I'm looking at a graph of F, not of the Y partial of F. So I can't take a graph point of view on this X partial. Useless. Right? Conveniently, we have this other point of view that you can visualize an X partial as being, well, look, it's the rate of change of whatever it is that you're looking at as you move in the X direction. So that's the point of view we'll be taking there. Now let's apply this to the picture I have down here, for which I'm going to have to zoom out. Let's see, here we go. That'll do it. There we go. Okay, so let's talk about Y partials. By the way, you're going to notice furthermore here, I didn't actually draw a surface. Right? This is just an art problem, but as y'all know, drawing three-dimensional pictures is hard, and there's tough questions that you experience of, sometimes the more you draw, the more clear your picture becomes, but eventually the more you keep drawing, you're just making it cluttered, right? And I feel like that's what happened here when I tried to draw a surface, but you could imagine a surface. You can almost kind of see a surface where these are tangent lines that I'm drawing, right? So use your imagination as to what the surface is. But that said, I reference that when you're doing Y partials, that means that you're going to be looking in the Y direction. I'm drawing Y partials at various different points here, but in each of these points where I want to look at a Y partial, I need to be moving in the Y direction. And as I'm moving in the Y direction, I need to ask what is the slope of the tangent line to the graph as I move in that Y direction. So each one of these here is intended to be kind of, if you will, sort of directly above one of these arrows pointing in the Y direction. So, use your imagination again there to visualize what I'm talking about here. Is that cool? Does everybody see what I'm? Okay. All right. So let's see here. Back to blue. So I'm looking at these slopes. That one there looks like it's about -2 ballpark, right? And then this one here appears to be about oh, come on, I can do better than that. About -1. This one's about -0.5. This one looks like it's about 0. This one here looks like it's about +0.5, perhaps. right? But nevertheless, anyway, each one of these blue lines up here is a tangent line in the y direction to my graph, which again would clutter my picture if I were to try to draw it. So, okay, those are the y partials. Now let's think about what the x partial is doing. And again, when I take the x partial, that just says I need to see how do these y partials change as I move in the x direction. So as I mean, each one of these individual tangent lines is its own little computation of a y partial. Now I'm going to ask, as I move in the x direction, as I come out of the screen, as it were, how are these slopes changing? And as we just kind of talked through, well, they're going from negative to less negative to 0 to positive. What I have going here looks like those y partials are increasing. So the rate of change in the x direction of these slopes appears to be positive. And so from what I have drawn here, we would infer this mixed second partial to be positive. This is what it looks like when you have a positive mixed second partial. And how would you describe this geometrically? The best answer that I have is it's a twist, right? It's like the surface. I like to imagine that someday I'll actually get a physical one of these, but I imagine a sheet of rubber, and that the sheet of rubber is literally being twisted like this. Everybody see what I'm doing? So just putting a twist in it. That's what mixed second partials measure, right? Unmixed second partials measure cross-section concavity. Mixed second partials measure twists. And again, there is no single variable version of this. It's a brand new geometric idea. And by the way, another piece of the calculus of graphs, because we're looking at the graph of or the undrawn, alluded to picture here is a graph of the original function f. So there was that. Was that you?
Yeah. So like just before this, we said that if it's f is of c to the k, that we can flip the order.
Yes. Isn't that weird?
Yeah. Is there any way we can apply that here?
Yeah. Totally. So you're right. I drew this as x partial of y partial. What this is saying is that gosh, this is really hard to visualize, but when you twist a sheet of rubber like this, you are also twisting it like this.
Okay. Yeah.
You see what I'm saying? And you got to kind of like use your visual imagination. And again, I don't know where to get a sheet of rubber. Where does one get that? Anyway, just look at the tips of my fingers, right? In some sense, this twist has two of my fingers are going up and two of them are going down, and that's the same exact thing that's happening this way. Yeah, that's a little bit of a hand waving, you might say, explanation. How we doing? Everybody good? Okay, so yeah, this is sometimes called torsion, but I like to think of it as a twisting. Okay, let's see here. Real quick, let's get started on 3.1. Oh, notice we're not done with Chapter 2, but I'm already introducing Section 3.1, and that's because there's some stuff in 3.1 that's going to be very useful when we get to Section 2.5, which is coming next. So anyway, a little bit out of order, but I do that in a few places. And remember parametric curves. Right? So position is a function of time. Notice this is a function that has in output variables, but only one input variable. Right? So t, the only input variable, and then several, x1 through xn output variables. So that being the case, there's only one input. That means the derivative matrix only has one column. There it is. It's all the I'm going to say partial derivatives with respect to that one input variable, but then we remember, wait a minute, if it's only one input variable, they're literally single variable derivatives. So that's why I use the D here instead of a partial. They're not really quite partials. Right? They don't have to be. Okay. So then you look at this expression. Let's see here. Here again is the formula for our. Oh, and I am out of time now. Okay, so we'll draw the line right there and pick it up here on Friday. Y'all have a good rest of your week till Friday.